Welcome to the latest episode of Mentors at Your Benchside. I'm Hannah Gamester, and today we're going to be talking about how fluorescent molecules work. Fluorescence is one of the most important and useful tools in a biologist's toolbox. In biology, almost every field, ranging from physiology to immunology, uses fluorescent molecules to detect proteins. However, the specific science behind how fluorescence works can be confusing or overlooked. Have no fear, in this article, we're going to break down the key points of fluorescence so you can be the expert you always wanted to be. So what exactly is fluorescence? By definition, fluorescence is a type of photoluminescence, which is what happens when a molecule is excited by ultraviolet or visible light photons. More specifically, fluorescence is the result of a molecule absorbing light at a specific wavelength and then emitting light at a longer wavelength. Thankfully, this topic is what Dr. Alexander Jablonski dedicated his life to. He eventually developed the Jablonski diagram to describe the absorption and emission of light. In short, the three steps of fluorescence are absorption or excitation, non-radiative transition or excited state lifetime, and finally fluorescence emission. The first step is excitation. So flashback to general chemistry. Visible light exists as elementary particles called photons. These particles are essentially packets of energy that, when absorbed, will propel or excite the light-absorbing molecule into a higher energy level. In the case of fluorescence, fluorophores absorb visible light, usually provided from an incandescent lamp or laser, leading to an excited electronic singlet state of the molecule. The second step is the excited state lifetime. As we all know, the goal of an atom is to be at the lowest energy state possible. So when a fluorophore is excited to a higher electronic state, it immediately wants to begin releasing energy. Therefore, this excited state, known as the excited state lifetime, doesn't last very long. It lasts only typically in the region of 1 to 10 nanoseconds. Even so, this step in the process is incredibly important, since it is during this time that energy from the excited electronic singlet state begins to decay towards a relaxed singlet excited state from which fluorescence emission originates. The third and final step is emission. And now we're finally ready for some fluorescence. Beginning at the relaxed excited state, the high-energy photon decays quickly towards the ground state and emits this energy as a photon of light. This transition of energy is what we know as fluorescence. Interestingly, because some of that energy was already released during the excited state lifetime, the energy of the now fluorescing photon is lower than the energy of the excitation photon. Thus, the energy released during fluorescence will always be of longer wavelength than that needed for excitation. So how does flow cytometry take advantage of fluorescent molecules? So when dealing with fluorescent molecules, we need to pay special attention to the difference between excitation and emission wavelengths or energy, which is otherwise known as the Stokes shift. The significance of the Stokes shift lies in its simplicity. It allows us to determine if the wavelength of emitted light and wavelength of excitation light is large enough for us to reliably tell them apart. As the readout of flow cytometry is based solely on fluorescence, it is essential to be aware of this parameter or risk generating unreliable, rubbish data. Moreover, it's extremely important to keep track of the absorption spectrum and emission spectrum for each fluorophore and how various lasers may interact with the fluorophore in question. For instance, in a flow cytometry machine, the argon laser emits 488 nanometers of light, which excites the fluorophore fluorescent isothiocyanate, which is often shortened to FITC. Because the 488 nanometers is very close to the FITC absorption maximum, excitation results in a high FITC emission. However, if FITC is excited by another wavelength from a different laser within its absorption spectrum, it emits light in the same spectrum, but it is not of the same intensity. So there you have it, a quick introduction or perhaps reminder of fluorescence and how it relates to fluorescence molecules utilized in flow cytometry. Check out the full article at Benchside Bio and subscribe for more help and advice from mentors at your Benchside.